Okay, thanks for the introduction. So good afternoon. My name is Zhaoming from Department of Computer Science, working on computer animation and robotics. So today I want to talk to you briefly about reinforcement learning and how I use reinforcement learning to make a robot or a virtual human in a simulator to walk. So before I tell you about reinforcement learning, I want to first show you an example of how reinforcement learning works in a real scenario.
What's this cartoon called again?
Oshikuru Demon Samurai.
It's not a cartoon, it's anime.
Anime. You know, I knew a girl in high school named Anime. Anime Fletcher. She was born with one nostril. Then she had this bad nose job and basically wound up with 3.
You're here a lot now.
Oh, am I talking too much? I'm sorry. Zip.
Thank you. Chocolate?
Yes, please.
So here he is reinforce her behavior using a chocolate as a reward.
Hey, Kim. Yeah. You know what? Hold on. Let me take this in the hall.
And then more reinforcement learning.
You'll never guess who they got to replace you at work.
Okay. I know what you're doing.
Really?
Yes. You're using chocolates as positive reinforcement for what you consider correct behavior.
Very good. Chocolate?
Sheldon, you can't train my girlfriend like a lab rat.
Actually, it turns out I can.
Well, you shouldn't.
There's just no pleasing you, is there, Leonard? You weren't happy with my previous approach to dealing with her, so I decided to employ operant conditioning techniques, building on the works of Thorndike and B.F. Skinner. Yet by this time next week, I believe I can have her jumping out of a pool, balancing a beach ball on her nose.
No. This has to stop now.
I'm not suggesting we really make her jump out of a pool. I thought the bazinga was implied. We're just tweaking her personality, just sanding off the rough edges, if you will.
No, you're not sanding Penny.
Are you saying that I am forbidden from applying a harmless, scientifically valid protocol that will make our lives better?
Yes. You're forbidden.
More reinforcement learning. So I hope you have some idea now about what reinforcement learning is. So basically it involves an agent acting in an environment, and the environment will give the agent some feedback by giving the agent some rewards. And so at the beginning, the agent is just doing some random thing in the environment without a care in the world, and then the agent will occasionally receive some good rewards and bad rewards. So once it receives a good reward from the environment, it will change its behavior and then try to get these good rewards more. And once in a while, it will get some really bad rewards, and then the environment will give, and then the agent will try to change its behavior so that he will avoid those kind of situations. So that's basically what reinforcement learning is. And now, so reinforcement learning has become very popular because DeepMind in 2015 released a program that used reinforcement learning to play Atari games all by itself. And then just last year, DeepMind released a program that used deep reinforcement learning to play the ultimate chess game called Go and defeat the world champion in this area. So it's very popular because of playing games. And then the reason that I really care about reinforcement learning is that it can help me to do some really crazy stuff in simulation. So here is the work that will be presented in this SIGGRAPH by Jason Peng. And this all simulation-based reinforcement learning. So while explaining this, I can explain why is this useful. So imagine you want to make an animated movie, or you are designing a video game, and you want to make a virtual human walk in your animated movie or video game. And then the typical way to do this is that you hire some artist, and he or she will draw a sequence of picture, and then you just play forward. Or you hire an actor, and then you place a lot of sensors on him or she, and then with a motion capture studio, you can capture his working data and then play forward in your animated movie or video game. However, this will do fine in an animated movie, but suppose you are controlling an agent walking around in a video game, and suddenly someone comes out and pushes him. And then how do your agent respond to those pushes? So one solution would be to collect more data that involves how a human is being pushed, but it will be really tedious, and you need to collect millions more of data. Another way to do that is to to do these things in a physical-based simulation. So when the agent is being pushed, it will just naturally fall down without any user input. So just by your physical environment, it will fall down naturally. But it will be really difficult to tell an agent how to walk in a physical simulated environment. But here is where reinforcement learning comes to the rescue. We can teach an agent to do all this kind of crazy stuff by itself using reinforcement learning. And here is some crazy motion that it can do, like spin kick. You can also do it for T-Rex, which you cannot collect data for because there's no T-Rex. And then look how they react naturally by the perturbation, because we are using a physical-based simulation. So this is all really amazing work. So this lion is really fun. Okay, so another application that's really dear to my heart is to make a real robot learn to walk by itself in the real world. And here is a robot that learns to walk by itself. Okay, speed forward. So here he doesn't learn how to walk yet, so he falls down, but he will get up. And can continue learning to walk, and then falls down again. So just fast forward. It's like after hours of training, he will learn to walk stably. So, but the problem with reinforcement learning is that it's really, really difficult. For example, for this robot, it takes a lot of time to learn that. And like Google DeepMind also tried to, oops. So DeepMind also tried to learn to walk using deep reinforcement learning, and it gets this crazy kind of motion. So you can't really expect a robot to do this kind of motion. Like the roboticist will say, "You are crazy, get out of my way." And the way the robotics do this is, so this robot, Alice, that just came out like 2 months ago, I think, can already do pretty good at walking by itself without any training. So this requires hours or days or months of manual tuning, engineering tuning, and it can already do a pretty good job, but the problem is it requires a very good expert to do that. And then more about how reinforcement learning is difficult. So while playing this video, I explain what this table means. So like to do a backflip in the video that I just showed you before, you need to train like 62 to the 10 million steps, and then 62 million steps. That's like days and hours of training if you want to put it on the hardware. And that will wear down the robot pretty fast. And you don't want to do that on the physical robot. And instead, Boston Dynamics show us last year that you can do this already without any training, but still that requires expert tuning and a lot of engineering effort. So why don't we combine the best of the two worlds? Like we can do training in the simulation that doesn't do any harm to the robot, and then we can directly try to use that controller that works in simulation and try on the real robot, and that doesn't require any expert tuning. So can we do that? So we are collaborating with people from Oregon State University and this company called Agility Robotics that's based in Oregon. And we are working towards using reinforcement learning to make this robot called Cassie work. So Cassie is named after this crazy bird called cassowary. I think that's how it's pronounced. And then, so here is some result that's in simulation. So yeah, so here we have a reference motion, and we are trying to imitate that reference motion using reinforcement learning. And the controller is really robust. Here he's blindly walking on a sinusoid terrain. And then the good thing about reinforced deep learning is that we can provide any input to the network. And here we just give it the terrain information, and it can learn to adapt to those different types of terrain. And now just some more video. So here is a controller that's slapped in place in simulation, and we try to transfer it to the real robot. So here is how it looks like. So we are getting there. We are close to getting a controller to transfer from simulation to a real thing using reinforcement learning. And yeah, that's basically it. And so if you have any question, I'm happy to answer.